Okay, so in this lecture, we'll be covering the idea of process synchronization. As I told you, it is one of the key topics in an operating system course, and we'll first try to motivate ourselves that why do we need to synchronize process. Though I have written the topic as process synchronization, but it is equally applicable for threads as well. So threads also need to synchronize. We'll first we'll see some background of this particular problem, the synchronization problem as it is called. Then we will look at the different solutions of this particular problem. We'll initially talk about the software level solutions, which were proposed by one of the well-known scientists in the domain of computer science. Then we'll see some hardware level solutions. And finally, we'll talk about the ones that are preferably used today and which are known to be the best possible way of handling this problem. It's the idea of semaphores, which was again proposed by Dijkstra's. We'll see what are the different what is an idea of a semaphore and how is it used to handle this synchronization problem. We'll end up this lecture with discussion on three classical problems of synchronization. One of the three very key problems of computer science. And finally, we'll also talk about another mechanism that is used today to handle this synchronization problem. It is a programming language solution. It's called monitors. So before we go into the details, let's quickly move to the basic background of this problem. What is the basic idea behind synchronization? Why do we need to synchronize? Now, as you know that when processes communicate, processes or threads for that matter, when they communicate, there are different communication mechanisms that we have learned. One of them is the shared memory. We just saw what a shared memory is. That it's part of the memory which is used by the two processes which would like to communicate. If it is P1 and P2, which would like to communicate, they make use of this shared memory segment. Process P1 writes, process P2 reads, or process P2 writes, process P1 reads. It can be in this way. So far, it is fine. The problem is if they have some shared data. And if there is some shared data that is to be used by both P1 and P2, it may result in some data inconsistency. This is one of the biggest problems that we have. Data inconsistency. Now you may wonder why at all we will be having data inconsistency. There will be inconsistency because these processes that you are working with, they would be working in a particular order, and that order is not known to you. That is the problem. What do you mean by that? We know that when we have a set of processes, right? When we have a set of processes, say P1, P2, P3, now the scheduler, it decides on which process to be given a chance to currently get executed. Is it P1 or P2 or P3? Right? Now think a situation where P1, P2, P3, all of them are using a shared variable. Let me give you an example. In fact, we will be looking at a motivating scenario. And let me start off with two threads which are updating a shared variable. It's a very, very interesting situation. And let me come to that first. Okay, this is the situation. Are you seeing this? All of you?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Let us assume that there are two processes or two threads, whatever it is, and they are trying to update a shared variable. Okay, the shared variable in this case is a variable called counter, which is of type integer and has been initialized with a value of 5. And here we have process number 1 or thread number 1, process number, sorry, we have an, this is process number 1 or thread number 2, and I should have written it here. This is incorrect. This is counter minus minus, let's see. Okay. So please ignore this. We have, instead of this, it is counter minus minus. So process 1 is running counter plus plus, and process 2 or thread 2 is running counter minus minus. Counter is, by the way, a shared variable. What will be the output of running process 1 and 2 or thread 1 and 2? What is the output? Yes. Remember that 1 and 2, they run in an interleaved way. This is how things are happening. Okay. The scheduler is first running, allowing 1 to run, then 2, then 1, then 2, then 1, then 2. In this alternate way, if you run, what do you expect the value of the counter?
The expected value should be 5.
Okay.
It's same only.
But
It should
it
be
may
5.
or may not be.
So you say that it is 5. All of you agree? Mithul says that it should be 5. All of you agree to that? Seems to be, isn't it? It should be 5.
Yes.
But it is 5 only if you strictly follow this alternate way of execution. If you strictly follow this alternate way of execution, you know that, okay, it is going to be 5. But the problem is that these instructions, these counter instructions, in assembly, they are not one single instruction, but you can view them to be a combination of 3 instructions, right? A combination of 3 instructions. So this counter plus plus is actually 3 instructions in assembly. Similarly, the counter minus minus is 3 instructions, making use of these R1, which are registers. So when you look at in more details, what is the operation that goes on for updation of a variable or for decrement of a variable? It's like the original value of the variable is first loaded onto a temporary register, let's say R1. Then the R1 is updated by 1, and the updated value is now becoming my present value. And finally, the updated value is written back to counter. This is what happens. Is that okay? This is the order of things when you want to do counter plus plus. Similarly, if you want to do counter minus minus, again the same thing. The initial value of counter is now loaded onto a different register, R2. Then the R2 is decremented and R2 is written back to counter. This is what happens. Well, let us assume that we are strictly following 1, 2, 1, 2 in this way. So if it is 1, 2, 1, 2, then the 1 means the counter plus plus operation happens, and 2 means process 2, where the counter minus minus operation happens. So if it is counter plus plus, that means all 3 instructions were executed. So initially counter was 5. So R1 became 5. Then R1 became 6, and then counter became 6. So process P1 was over. Then there was a context switch. Context switch means process 2 started. Process 2 started, When process 2 started, counter was loaded onto R2. So R2 became 6. Then R2 decremented itself. So R2 became 5. And then finally R2 was loaded into counter. So counter here became 5, which is shown as that. Okay. Clear, everyone? Is it clear to everyone?
Yes, sir.
Okay. Now, the problem is that these three statements, these 3 and 3, 6 statements, if they happen in the order in which we have written, you expect a definite output which is 5. But these 6 statements, they may happen in different order. There may be a situation where you may have this kind of a ordering, where the first line of counter was executed. So P1 was executed, process P1 was executed, this one was executing, this line was executed, so count R1 became 5. Suddenly there was a context switch. You don't know when the scheduler will pick up one process and give it to the other. It gave it to. So P1 was taken out of the CPU execution and P2 started executing. Okay. So if P2 started executing, counter has not yet been updated. So what is the value of R2? The counter is still 5, remember. Counter is still 5. So counter is 5, so R2 is 5. R2 decrements itself, so R2 is 4. Then counter becomes 4. No problem. Then again there's a context switch. And you come back. So during this time, P2 was executing. Then again there's a context switch and you come back to P1. What was P1? P1 was left with the last 2 instructions which were not executed. So now it will execute that. So what is R1? R1 is the previous value of R1, which is 5. And it updates itself. So R1 now becomes 6. And counter gets updated by value of R1. So counter, which was previously 4, due to execution of P2, now has been updated to 6. So counter becomes 6. See. So due to this ordering, the process which was finally updating counter is the one that is deciding what will be the value of counter. Look at this scheduling pattern. Here it's just the reverse. Let us assume that initially P2 started the execution. So counter was 5, R2 became 5. And then there was a context switch. That means P1 started executing. And P1 could complete all the 3 instructions. So R1 became 5 here, which was the initial value of counter. R1 became 6. Counter became 6. Then there was a context switch. And again, we started executing P2, which means R2 again became what was counter. The counter value was, no, this is not there. This line should not be there because this line is, let's say, already executed. So let's assume that P2 starts execution from here. So R2 decrements itself. So R2 becomes 4. And then counter is updated by this value, which is 4. Now see the problem. If this is the scheduling pattern where P1 started, it executed one line and then P2 completed and then P1 came back, you get the counter value 6. And if it is the other way around, you get the counter value 7. Or sorry, counter value of 4. Right? You get the counter value of 4. But if this was according to this order, you would have got the counter value 5. This is the trouble. The trouble is that if there is a shared variable and there are multiple processes or multiple threads that are updating that particular variable, the ordering of the instructions, that determines what will be the final output. And the problem is that this ordering is not in your hand. It's decided by the scheduler. Now there's the problem. So we are now handicapped because the scheduler decides which process will run, and there can be any ordering. And now that we have a shared variable where every process is sharing something with any other process, and if both processes execute and do something or write something to that particular variable, you end up into a trouble. This is the race condition. This is the race condition that we are talking about, right? And here that we have this particular, I should have written it here as 4. This is the problem of synchronization. Now think that if this is not only for a shared variable, it can be for a shared data structure as well. Let's look at this. Is the problem clear to everyone? Any
Yes.
questions? So whenever you have a shared data or a shared data structure that will be shared among a lot of processes or threads, and each one of them are updating it in their own way, the problem is that at the end of all the execution, you cannot deterministically say what is the output. This is called race condition. It will be a problem because the scheduler will decide who will schedule and which process will execute. Since it is not known to the user, you will not be able to decide what is the final result. So let's look at the situation again. So let's look at this particular. This is a problem which is known as bounded buffer. We saw a problem where we had 2 processes updating a data. In this, we are going to talk about 2 processes handling a data structure. And the data structure we are talking about is a bounded buffer. Okay, this was the problem that was given to or was conceived by the famous computer scientist. We are aware of his name. I don't know how many of you know him. He is the person who gave this particular problem, Dijkstra's. Have you heard of his name?
Yes, sir.
Yes, sir. Garage algorithm.
In data structures?
Yes, sir. In graph algorithms.
The
shortest path algorithm.
Right? So Dijkstra's, as well as one more scientist whom I'm going to talk about later on, are the ones who are pioneers in this field, who gave these problems and their solution. So let's first talk about the bounded buffer problem as given by Dijkstra's. What is the problem? The problem is that there are 2 processes. One is called the producer process, and the second one is called the consumer process. Producer process is the one that produces items and keeps them in some buffer. Now let me give you a problem. Here is a producer that produces items, and here is a consumer that consumes items. The problem is that producer and consumer, they are not working at the same rate. They are not working at the same rate. Right? Producer can produce items quickly, consumer does not consume items. So if that is the situation, what can be the problem? Suppose producer is producing items very fast, consumer is not able to consume items. What can be the problem? Let's buffer overflow. I'm not coming to the buffer. For the timing, let's assume that there is nothing. Just a producer is producing and consumer is consuming. Now, what is the problem that can happen? Data loss. Producer is able to produce many items, but consumer is not able to consume them. So some of the items produced by producer will be lost. Right? Just think about some files, some data being generated and sent to the printer. So the computer is the producer which is sending some data and sending it to the printer. But the printer is not working at the speed of that particular buffer or of the computer. So some data will be lost, some characters will be printed, some will not be printed. Okay, it's a problem. So what to do? We will introduce a storage in between and we'll call that as a buffer. So I will have a buffer. So producer will produce items and will keep it in the buffer. Consumer will be consuming it from the buffer. Now Dijkstra's gave two versions of this problem. In the first version, Dijkstra said that this buffer would be of infinite size. Okay, it's called unbounded buffer. So if it is of infinite size, then there is no problem. Producer can produce in own rate and can keep it, and consumer can consume when it feels. So there is no problem. The challenge is when the buffer is bounded, that is, the buffer is of a finite size. For example, the figure that I've shown here. In this case, the buffer is of size n. That means you can at max hold n items in that buffer. So what we have defined is, we have defined a variable called n, and we are defining an item of certain type, which is generated by the producer. And there is a buffer, which is an array of n items. Let's assume that. And let us try to model this as a programming problem. So what are we doing? We are looking at in this, the producer is producing items. So it's a while one loop. That means producer is always on. It's always doing something. It is producing an item. Let us say the item that it's produced is next P. Okay. And I'm trying to find out that producer is producing items and keeping it in the buffer, and consumer is consuming them. So let me define two processes, a producer process. So a producer and a consumer process will be working together. What is the job of the producer? To produce an item. Let's call this next P. And what am I going to check? What is the check that I have to keep? Anyone? What are the two things the producer is going to do? What should a producer process check?
If the buffer
Buffer
is
size is not a button.
Pardon?
if the buffer is full, they do not produce anything.
Correct. So the requirement of this particular producer is that if the buffer is full, it cannot produce any item. It should not produce any item. Why? Because if it produces any item after the buffer is full, that item will not have a place to be kept and that item will be lost. So remember, the condition is for the producer, your check should be whether the buffer is full or not. Okay. So what is the idea behind this? You check whether your particular thing is full or not. So this is the condition that I'm checking. Now what I'm doing is I'm using two pointers, in and out. Producer is checking something through in and consumer is checking something through out. Okay. Now what I'm checking is I'm checking the value of in, the current value of in. You can think in to be a pointer that is moving from here to here. Okay, is moving from here to here. That's the value of in. So in is actually the index of the buffer. The current value of in is the empty slot where you can put the item produced by the producer. This is what is done. This is where you are putting the item in the buffer. So obviously the index in is deciding which is the empty slot. And then you are incrementing the in so that you can point to the next one. Now what you are checking here? You are checking as long as in plus 1 mod n. Mod n means because at max you can have n, so you have to take mod n. is equal to out, you do no operation. That means if, let's say, the value of out is n, okay, if the value of out is n and your input pointer, that is finding out the empty slot, has reached here, that means you have no more slots. So you should do no operation. You should not produce anything. Keep quiet. Right? So if you find that n plus 1 or in plus 1 mod n is equal to out, you do no operation. So I am using in this particular code a pseudo notation, which is somewhat mix of C as well as some English text. So this is not any specific programming language. We are using a pseudo notation. So the idea is that we are finding out if this input pointer is equal to the output pointer. So the input pointer is initially 0 and the output pointer is n. So you're trying to find out whether it has reached n or not. If it is n, that means you should stop. You should do no operation because the buffer is full. What is the other way around? What about the consumer? What should the consumer do? What should the consumer check? The producer should check whether the buffer is full. This is the check that the producer should do. What should the consumer do? What should the consumer check? Anyone? What should the consumer check?
Consumer will check whether there is data to consume or not.
Yeah,
Yes.
empty.
That means if the buffer is empty, there is no item that is currently in the buffer. That's what the consumer will check. When will that happen? Suppose initially the value of out is 0 and the value of in is also 0. When this will be the case, then you do no operation. Okay. So this is a while loop, which if this condition is true, you do no operation. If this condition is not true, then whatever be the buffer out, that you keep in next C and then you increment. Next C is the one that actually gets printed. It's a typical solution that as a very naive solution. Okay, you keep a buffer, producer has a pointer that keeps the empty slot, consumer has the buffer that keeps the filled slot. If all of them, producer keeps track of the number of filled slots so that whenever there's an empty slot available, it puts it there. And consumer keeps track of how many of them are, if they are all empty. If there is at least one filled, it consumes them. Simple. That's the solution. And this buffer is in the shared memory. That is why it's a shared memory solution. Can anyone identify a problem in this solution? Is there any problem in this solution?
The busy wait is not atomic. We can use make the busy wait, the while condition do no op. So we can make use of the semaphores or locks around it.
Let's look at the problem. The solution that is proposed here that allows at most n-1 items in the buffer at the same time. Okay, it allows n-1 items in the buffer at the same time. Now let us try to modify this deficiency by introducing a counter variable. Let's look at the counter variable. Okay, let's see the problem. Here we go. Now we have a counter which is used along with the same item and buffer and n. We have introduced something called counter. And here is what we are keeping track of in the process, in the producer process. So this is the test whether the buffer is full. Is that okay? This is what you have to check. So if the counter has reached n, that means all the items in your buffer are filled. All the slots in your buffer are filled. If it is filled, then the producer should do no operation. It should keep quiet. But if it is not full, Then you do what you do. The current value of in of buffer, there you put next p, the item that you have created, and you increment in, and obviously increment counter as well. That's what you do. What do you do in case of the consumer? In the consumer, you check whether buffer is empty. How? Whether buffer is empty by comparing whether counter is equal to 0. Okay. Is it clear to everyone? We just introduced a variable called counter, and producer checks whether counter is n, consumer checks whether counter is 0. If counter is n, producer will keep quiet, will do no operation. If counter is 0, consumer will keep quiet because there is no item in the buffer to consume. In the producer, counter is incremented by 1 in every iteration, and in consumer, counter is decremented by 1 in every iteration, because after all it's reducing, right? That's what the idea is. Is the code clear to everyone? Okay. A practical example of this particular code would be, I'll show you. Let's first try to find out what is the problem. It's the very, very similar race condition problem that we have seen in case of the threads in the two processes. Remember, we could not say what is the final output of the process. Is it 5 or 4 or 6? The same thing happens here. The producer has a code that produces the counter plus plus, and the consumer has a code that has counter minus minus. That's the problem. Again, it's the same problem. So if you initially start with 10, your producer would have this relation counter plus 1, and your consumer will have this relation counter minus 1. So at the end, and if your counter plus 1 is equivalent to these three relations, and similarly your counter minus is equal to these three relations, you end up into a final value where you can have all possible values of counter. It can be 9, it can be 10, it can be 11. And it depends on the order in which these 6 statements are executed. That's the problem. If you execute in a particular order, you will get 10. In another order, you will get 9. In another order, you will get 11. This should not be the case, because there should be a deterministic result. You cannot have ambiguities. This is the situation which is called race condition. What is that? The situation is where several processes, they access and manipulate the same data concurrently, data or data structure. And the problem is that the outcome, it depends on the particular order in which the accesses take place. This should not be the condition. If you do that, you end up into trouble. Let me show you with a practical example. A practical example is this. Suppose this is the spooler directory, which is maintained in the printer. So all the processes that you want to print, they are again placed in a buffer, the spooler, and that's again a shared data structure, queue. Now, if that is the current value of the queue is maintained by this particular variable called in, which is maintaining the next empty slot, where a new process which is going to print something will place its value. Now, if both process A and process B are targeting this same empty slot, because both of them are maintaining in. Now, let's have a look at the code. Look at this particular code, which is a request for print. Whenever you click print, it actually goes into a buffer, and the job is kept in a spooler. And accordingly, the printer takes one by one the job from the queue and prints it. This is one such code that is shown here. So add file to the print spool takes as an input the name of the process. And these 3 lines have to be executed. Now suppose process A executes line 1, which is like in load into local in. Then process A is preempted and process B starts. Process B again loads its input into local in. That's fine. It completes everything and finishes off all the 3 statements. Then again A starts. And the problem is that whenever you are finally storing that, which is this, okay, when A starts, A has actually placed in the spool its name. So what has happened? B had created its own copy of in, but that gets overwritten by A. So process B's file will never be printed. That's exactly the same thing. That is the other 2 motivation examples that we saw. Everybody was reading the counter, but the problem is the counter was updated. The process that was finally updating the counter, that value gets printed. And you don't know which will be that process which will finally be updating the counter. Similarly, if both process A and B are writing into that empty slot, you don't know which process will print in that empty slot. In this case, as you see, process A is the last one to be touching that particular empty slot. So process A's file will get printed and process B will never be printed. This is the problem, right? I'll show you again with one more code that will make things easier and more better. Okay, let me show you with let us look at this code, badcount.c. Are you able to see this?
Yes.
Okay. Can anyone tell me what is going on? What is going on in this code?
We have
Have a
2
look at the
threads.
code.
We have 2 threads that are accessing the shared memory, which is represented by CNT variable, and they are updating the same variable.
Yes. This is the shared variable called count. Okay. This is the function that I want the thread to execute. Listen to my words. This is the shared variable called CNT, which is initialized to 0. And this is the function that every thread would perform. What will the thread do? It will run a loop from 0 to NITR, NITER. NITR will be provided somewhere. And will just increment the value of count. That's what it's going to do. Now, in the main, I have used 2 threads, TID1 and TID2. And I have used pthread create, and pthread join. So this is for pthread 1. This is for pthread 2. I have joined pthread TID1. I have joined TID2. Interesting part is here. If the count is less than 2 INITER, I should print this line. Okay. Else I should print this line. And then I exit. Let me run this. Oh. My count is coming out to be 1482220. Can you tell me why? It should be this value, but I'm getting this value.
Race condition.
Race condition. Absolutely. Why? Because NITTR has been declared as 1 followed by what? This is 1,000, 1 lakh. So if both processes or both threads had run 1 by 1, I would have got 2 lakh. That's what it is saying. you should have got this result had everything been done sequentially. But this is not happening. Sometimes maybe process 1 or thread 1 has written count to be 5, and then suddenly thread 2 starts. Thread 2 updates everything and makes count back to 1. Again, everything runs for some time. Then again, there's a switching, and then again, thread 1 resumes and thread resumes from 5. So in this way, you may get different kinds of combinations. And finally, you see, this is the value that you are printing. Next time you run once again, you will get some different value. Look, you this time get more than this, 1,49,611. But never you are getting this. You're not getting this. So that is the problem. Both of them are touching that particular variable, and I don't know whether they are going to run in a proper order. This is the problem that we have, right? So if this is the problem that we are facing, how to solve that? Well, for that, Dijkstra's came up with some idea. Now I'm going to introduce you to the idea today, and then we'll take up details tomorrow. What is the idea that Dijkstra's gave? This is what Dijkstra's introduced to the world, that this is a problem and we need to solve this problem. And he defined this problem, or called this problem, the critical section problem. So what he said is that whenever you are talking about n processes, and all of them are trying to use, there is a particular segment in their code, there is some part in their code where they are trying to share some data object. That data object can be a variable, that can be a table, that can be a file, that can be a buffer, anything. So that particular portion of the code where every process is touching that particular shared object, we will be calling that portion as critical section. We are not interested to know whether it is a table or a file or a buffer. We know that it is a shared thing. So if there are a number of processes, and somewhere in that there is a portion where there's a shared code that is used, whether it is P1 or P2 or P3, everybody somewhere has used this counter, maybe the counter. So this is the variable in this case, which is shared. It can be a data structure like a buffer. So whatever be the case, the particular thing that is shared, the portion of the code where which is very, very critical, which is shared among a lot of processes, we will call that as a critical section. Remember this, we will be using this term now. Now, Dijkstra said that if you want to avoid this race condition, you have to allow only one process to use the critical section at a time. And it is called mutually exclusive in time. So if you are using a shared data structure or a variable or a file or a buffer, whatever, only one process will be allowed to touch that. That is, only one process will be allowed to execute the critical section. All others will not be allowed. This is the problem of critical section, or we call it the critical section problem. So we have to design a protocol that will be utilizing all the processes that are in use. And each process, what is the protocol? There are a lot of processes, all of them want to go into the critical section. Going into the critical section means they want to execute the critical section. Critical section means the portion of the code where they will be writing to the particular shared object. So the rule is, listen to this very carefully, the rule is that every process has to request to enter its critical section. Just because there is a process and there's a critical section doesn't mean that every process will be able to go into that. No. you have to request to enter the critical section. What is this request? Some additional code that you have to put in your process. That additional code is the request code. So all processes now which are going to execute the critical section should have an additional code in their process. That additional code will be the request code. That additional code will be divided into two sections, entry section and exit section. Let me show you the basic structure. This is the idea. Every code will have an entry section, the critical section, the exit section, and then the remaining part. So these red ones that you see here are the ones that are additionally put in the process. They have nothing to do with the execution of the code. It is just that they would ensure that only one process will be executed at a time, or one process will be entering the critical section. You will see different attempts. Is this concept clear to everyone? This is the idea of mutual exclusion. Remember, if you want to ensure, or if you want to guard critical section, that is, if you want to ensure that only one process executes the critical section, that is the shared data or data structure, you have to ensure mutual exclusion. Look at this situation. This is process A. This is the part of the code of A where it is supposed to execute the critical section. So A enters the critical section. We say that A enters critical section at time T1. A is entering critical section. At the same time, when A was executing, B also tried to enter critical section. Our solutions should be such that if A is currently executing the critical section, even if B is attempting to enter, B should be blocked. B should be blocked. When will B get a chance? When A has left the critical section. Let me give you an example. In the operation theater, the doctor is supposed to perform surgery on only one patient at a time. But there are many patients who are there. So the rule is that I will take that patient into the operation theater and then I will light a bulb to demarcate that I am currently working on one of the patients. All patients who also want to enter the operation theater should wait outside. When I'm done, I will turn that light off to demarcate or to signal that I'm done with the current job. Now the next person can come in. This turning on the light and turning off the light is that additional signaling procedure that I have to keep. This is that entry section and exit section. Okay. So this entry section and exit section are also called lock and unlock. So every process will have that. And you may wonder why every process will have. Yes. It's like a lock that you are given. The process that is currently in the critical section will first lock that, then enter the critical section, and then when it comes out, it will unlock that so that others can come in. But only one process will be allowed to get that lock. That is the rule. Not more than one process will get it. So one process, since it gets the lock and the one which gets the lock locks it, if it locks, that means no other process is able to enter the critical section. So the critical section is safe. As long as I am the process that is working in the critical section, nobody else is going to get it. That's what I do. There's a question in the chat box. How are the priorities of these processes determined? Well, priority is a different thing. It's decided by the scheduler. We'll come to that. Priority does play a role in locking, and it can create a problem. I'll come to that tomorrow. So for the time being, is the concept clear? There should be mutual exclusion. Mutual exclusion means only one process will be allowed to enter the critical section. How? We will add some piece of code before and after the critical section, so that that piece of code in every process will decide who gets a chance. Okay, right. Now, let me again go back to my code and I'll show you today, and finally I will end up this lecture with this code. Yeah, you saw bad count, which was not able to give you the correct result. Let us have a look at another program called good count. Let's see what we have done here. Same piece of code, no change in the main. The change is in this part. Can you tell me what is the change?
Now we are using locks.
We are using 2 additional lines. Can you tell me which 2 lines we are additionally using?
We set mutex lock.
Second and the last one.
Unlock.
Yes. So there is a line before this for loop. Why before this for loop? Because this is the critical section for my code. Why it is the critical section? Because in this part of the section, I am making or writing to my count, which is this shared variable. So this is the critical section of my code. If this is the critical section of the code, I have to protect it. I have to guard it. And this guarding will be done through the entry section, or we often call it the lock. I will lock this here and I will unlock this here. What is this lock and unlock? We'll take up this tomorrow. It is a mechanism through which you will be ensuring that only one process is allowed to execute the critical section. That is, you are going to ensure mutual exclusion. This is the idea that we are going to take up in understanding further the synchronization of processes and threads. So I stop it here today, and tomorrow I'll be taking up the class and we'll continue with the discussion on process synchronization.